Okay, so now let's look at some miscellaneous functions which are going to be quite useful. So let's consider set of labels that you might use for a classification problem. So they are, let's say, for some 6 data points, they are red, green, yellow, another yellow, and say red again, right? So you want to find out what are the unique labels. Here it's obvious there are only 3, but np.unique can be a useful function. It will come to our rescue when we need them. So there are 3 unique labels as seen from this, right? If you want to find out the number of these labels, then you can use shape of this, that will, and take the first element. It will give you the number of unique labels, right? So this is np.unique of y. Another function is np.maximum. Let's say you have 2 arrays, np.array of say 1, 10, minus 5, 4, 3, and another array, let's say np.array of 3, minus 3, say 4, minus 1, and 2, right? And you want to find out the maximum, element wise maximum among these 2 arrays. So you can use np.maximum of x comma y. So notice that it will compare the elements in the 2 arrays element wise. The corresponding elements will be compared, and whichever is the maximum, that will be retained. Okay, so next we come to max. So if you have an array, let's say 1, minus 10, 20, 0, 3, and you want to find out the maximum, then what you can do is you can use np.max of x. So that will give you the maximum. And if you want to find out the argmax, so the argmax of x will be 2 here, right? So 0, 1, 2. So that is the argmax of x. Now you can likewise do np.min of x, that will give you minus 10, and np.argmin of x will give you 1, because it's at index 1. You could also do this using x.max. Okay, x.argmax, both of them will work. Okay, so that is max, min, maximum, max, argmax, min, argmin. You can also look at sorting. Okay, so let's say you have np.array of let's say, now let me, we are familiar with the random number generation process, right? So let's say rng is np.random.default underscore rng, and let me generate integers randomly from say minus 10 to 10. Okay, let me generate say 20 such integers in this range, and let's call that x. So x turns out to be this. Now we want to sort. So how do we do that? np.sort of x. So that will give us the integers in sorted order. You could also do np.sort argsort. So that will give us the indices corresponding to the sorted array. Okay, so these are sort and argsort methods. Okay, so this functions max, min, argmin, argmax also work on arrays of more than one dimension. So let's take an example. np.array of, let's say 1, 3, 0, and say minus 1, 4, 1. Okay, so what do I want to do now? I want to find the maximum along axis 0, right? This is like top to bottom. M dot max axis equal to 0. What will that give me? That will give me the maximum along the axis 0, meaning it will compare 1 and minus 1, meaning it will compare 1 and minus 1, and 1 is bigger, so it will retain 1. It will compare 3 and 4. 4 is bigger, so it will retain 4. And in terms of 0 and 1, so if you compare those two, 1 is greater. So notice that one comes from the first list, or rather the first row. The 4 here in the output comes from the second row, and the 1 comes from the second row, right? So the maximum operation happens across the rows, or from top to bottom, okay, along axis 0 to be more precise. So what will this be if it is axis equal to 1? Notice that it's the maximum along the across the columns. So the maximum here is 3 in the first. So in that first row, the maximum is 3, or rather, instead of putting it that way, from left to right, the maximum is 3. From left to right, the maximum is 4, right? In the first row, it is 3. In the second row, it is 4. Okay. So that is some of the use cases of these methods. You can do them across a specific axis. Now we come to comparing arrays. Let's say there are two arrays. So there's np dot array of 1, 2, 3, and y is np dot array of 1, 2, 3 again, right? Now you want to compare these two. So traditionally we are used to comparing objects in this way, right? In Python. So xw equal to y. This is fine. Xw equal to y would return a Boolean array. Okay, but there is an issue with using this comparison somewhere else. So when do we use such a where do we use such a comparison? In an if block, right? Let's, for example, if xw equal to y, then do something, right? So print works. This works, right? So this is what we would like to do. Let's see if this works. Unfortunately, this doesn't work, and the error is that the truth value of an array with more than one element is ambiguous, right? So you have multiple elements here, right? So this is kind of tricky. So how can we fix this, or what can we do to fix this? Now there is this method called array underscore equal. Okay, np dot array underscore equal. So if you pass two arrays that are equal, that will return true. Okay, so let me copy these two arrays, paste them here. If they are equal, it will return true. Let's change one to say maybe something like 3.1. It's false, right? Even if one element is different from the between the two arrays, even if one element is different, this will return false. So this does an element wise comparison. Only if all the corresponding elements are equal will np dot array underscore equal return true. Now what we can do is, if np dot array underscore equal of x comma y, do something, right? So this will work. Sometimes we might not be interested in exact equality between two arrays, especially when we are doing floating point arithmetic, right? When we have to make approximations, you can't expect exact equality. So let me take an example of this, right? So let's say you have 1, 2, 3, and you have np dot array of 1.01, 2.01, and 3.01, right? So these are close. Okay, these are close to each other. They are not exactly the same, they are close. So in such a situation, if you want to compare two arrays and if they are close, you want to kind of say that roughly they are the same arrays, right? So they are not the same arrays in the sense that they are not equal element wise, but for practical purposes we can treat them as equal. So what are we doing? We have two arrays, 1, 2, 3, and y is quite close to it. So we tried np dot all close, we pass the two arrays. So the relative tolerance we set it to 0, and the absolute tolerance we set it to say something like 0.1. So if the difference between these two element wise, right, what is it here? In this case it's 0.01. 0.01 is smaller than 0.1, so this should hopefully return true. Okay, and that's what happens. So this returns true. Let's see what happens if we try 0.001. Clearly this difference is 0.01, which is bigger than the tolerance, therefore this is going to return false. Okay, so you can read up more about np.allClose later. You can add the question mark, run it, and see what happens. So what is the role of rtol, atol? But we will stick to atol equal to some value, and if you, so depending on what atol is, the closeness between the two arrays will be determined by the value of the tolerance. Okay, finally we'll come to higher dimensional arrays. So we have studied 1D and 2D numpy arrays, vectors, matrices. Now we'll study higher dimensional numpy arrays. So to help us with this, we will look at an image data set. So first import matplotlib.pyplot as plt. Okay, and we'll also import from keras. So this is a library that we are going to use for extracting the data set of interest. So import mnist. Okay, so we are now extracting the mnist image data set. Okay, and let's see what we have. So mnist has load data method that will load the training and test data. So this is of the form train comma test. Okay, so let's look at train. What is train? First of all, what is the type of train? It's a tuple. Okay, so what is length of train? It's 2. So there is a train of 0, train of 1. So what is train of 0? It seems to be a numpy array. What is the shape? 60,000 cross 28 cross 28. What is train of 1 dot shape? 60,000. So what does this mean? So in this case, train of 0 holds the data. Okay, so there are 60,000 images, each of shape 28 cross 28. So 28 cross 28 pixels, and there are 60,000 corresponding labels. Okay, now we can run np.unique on the labels, so train of 1, to get a sense of how many unique labels there are. So there are 0 to 9 corresponding to the 10 digits. Okay, so what we'll now do is we'll visualize one of these images. So maybe train of 0. What is train of 0? So train of 0 is the first image. Okay, so sorry, train of 0 is the entire data set, right? So train of 0 is the entire data set. Let me call it x. So what is x? It is the image data set. Okay, y will, if you call, so if you call y as train of 1, then y will have the label. So x dot shape and y dot shape, that would be this one, right? Now let's look at the image, one image, so x of 0, let's say. So what is x of d 0 dot shape? That is 28 cross 28. So we can visualize this as an image, plt dot im show x of 0. So this is a grayscale image, meaning there is only one channel. It's a black and white image. So we are going to visualize that. This turns out to be a 5. So is that the correct label? Let's look at y of 0, and it is 5 indeed. Okay, so now let's say we want to visualize image of a 7. How do we do that? So y double equal to 7. Remember that this will return a boolean array. It will be true, the element will be true if the label is a 7 and false otherwise. Okay, so we are now going to index into the data, so the features, the x matrix, or sorry, the x numpy array. It's not a matrix, x is a 3-dimensional numpy array, right? So the first index, remember, or the 0th index runs over the images. So there are 60,000 of them, right? So that is for the images. So I am indexing into that. Okay, I am boolean indexing or advanced indexing into the 0th axis of the numpy array, 3D numpy array x. The other two I am retaining as they are. So what this will do is this will extract all those images corresponding to label 7. Okay, so I'll call them x underscore 7. So what is the shape of this array that you expect? So what do you expect? So if you look at the shape, it will be some 6265 cross 2828. So 6265 images are there that correspond to label 7. So let's visualize one of them. Let's say x7 of 100th image here, plt.im show. This image I'm going to visualize using, it's a grayscale image, so gray. Okay, so this is 7. So if you change this, you'll get, so 101, that image is this. So 10th image is this, 7th image looks like this. Okay, so I hope you get the idea of how to work with 3D arrays. It's a very basic idea that I've given you. Now let's say, so let's go back to the original array of shape 60,000, 28, 28. Now if you want to do classical machine learning on top of this, what you would have to do is you would have to treat it as a tabular data set of size d cross n. Okay, so what is the value of n here? N is x dot shape of 0, right? That is n. Now let's say I'm lazy and I don't want to figure out what d is. So d is actually what? 28 cross 28. But let's say I'm lazy, so what do? I reshape this as n comma minus 1. So my numpy will now have to figure out what this dimension is. So let's call this x reshaped. And what is x underscore reshaped of shape? What is the shape of this array? It's 60,000 cross 784. So this is n cross d. If you could, what you could do is you could take the transpose of this, and that would give you a d cross n data set. Okay, now you have to be careful about one thing. So recall that discussion on view and copy. So is x dot reshaped a copy? Let's look at it. So let's try to ask, is x underscore reshaped dot base, is it none? It isn't. Okay, so it's not a copy, it's a view. So if you change x underscore reshape, then that is going to affect x also. So you have to be careful here. All right, so that completes our discussion on NumPy arrays. So this was the 5th NumPy notebook, and with that we are going to close this section. Thank you for watching.